Hey guys, welcome to another video. Now today we are going to start talking about surds. So what we're going to be ultimately working up to in this video is to look at firstly defining what a surd is, as well as carrying out these simple operations with these surds. So our adding, subtracting, multiplying and dividing. So first of all, before we even get into anything here, we have to ask ourselves, what is a surd? Now, the definition of what a surd is before we even get to that, we have to start thinking about these numbers that we looked at before when we did fractional indices. These were these rooted numbers, these numbers with square roots attached to them. So let's compare these two values here. Now, to understand what is a surd and what is not a surd, we have to look at the number within the square root. So if we remember when we dealt with squares previously, we defined this idea of a perfect square. Now, a perfect square is a number that we get from multiplying two of the same numbers. And these perfect squares, so 9 for example, is one of these. Because if we think back to what we did in the content from about a year ago, is that we get 9 from multiplying 3 and 3. So if a number can be multiplied by itself to give us a perfect square, we can apply what we call a square root to that perfect square to give us the number that multiplied by itself to give us that. So for example, if we take the square root of 9, that gives me 3. So this is kind of the opposite operation. So taking a square root of a perfect square gives me the number that was multiplied by it to give me 9 in this case, for example. So this root 7 here, this is where things start to get a little tricky, right? Because up until now, we've learnt these perfect square numbers, but our 4, our 9, our 16, our 25, etc. But we come across these other numbers, you'll notice the majority of numbers are actually not perfect squares. Between, say, 1, 4, and 9, there are a bunch of numbers that aren't perfect squares. Now, 7 is one of them. Now, there are two numbers that multiply that are exactly the same, that multiply to give us 7, but they're not exactly the same. We can make pretty much any number out of multiplying two of the same numbers, but they don't end up being very nice. Now, if you guys have a calculator at home, pop in the square root of 7. See what you get. What you will get is a number like 2.645, etc. And you're going to get a whole bunch of decimal points with no actual rhyme or reason to them. There's going to be no pattern that arises, and there's going to be no recurring number. There is no rhyme or reason to the decimal. Now, we actually have a name for these types of numbers. Well, the number we got here, 3, this is a really nice number. This is what we call a rational number. It behaves very well, as like a rational person would, for example. An irrational number is one, which we've defined this a while ago, but I'll redefine it. An irrational number is just a number with decimals that have no ongoing recurring pattern. So I can see 3, 6, 4, 5, and if I read it out further from the calculator, I get 3, 6, 4, 5, 7, 5, 1, 3, 1, 1. You can see there's no actual pattern here. So this is where surds come in. So surds are these square rooted numbers which produce an irrational number. So this, for example, is a surd. My square root of 7 is a surd, and my square root of 9 this gives me back a rational number, so this is not a surd. Apologies for the rain outside, it's very loud if that's coming through the mic. Now, a surd in essence is any square root, any number with we define this as a radical or a root. Now, all of these surds are any number with a square root that doesn't produce a rational number, that produces an irrational number. That is what we think of as a surd. So let's look at a couple of examples of this. So for example, let's just classify what is a surd and not a surd. So let's say we wrote the number square root of 16. Now 16 is a perfect square because I can get one rational number that multiplies by itself to give me 16. See, now we're extending the definition of a perfect square. The number that multiplies by itself has to be rational. That is the main idea here. So I can get 4 multiplying by 4 to give me to give me 16. So taking the square root of 16 gives me back a rational number of 4. So this is not a surd. What about the square root of 15? Well, 15 is not a perfect square. So if I pop in the square root of 15 into my calculator, I get 3.87298, etc. There is no rhyme or reason to this number in terms of the decimal points. So this is going to be an irrational number. Therefore, this will be a surd. Let's try maybe 2 more. If I have the square root of 71. Pretty clearly 71, from what we remember with our perfect squares, this is definitely not 1. So when we take the square root of 71, we're going to get an ugly number. So I get another surd. Looking at root, let's say 81, well, 81 is a perfect square because 9 and 9 multiply by themselves to give me 81. So 81 is in fact a perfect square, and when we take the square root of a perfect square, we get a rational number. So root 81 is not a surd. So now that we've defined this, let's look at some simple operations we can do with surds. Now, let's look first at addition and subtraction. Okay, now what if I had an example here where I had 2 root 3. Now this is a surd. This is just saying 2 times root 3. I'm writing this shorthand as I would in algebra, if we remember. To say 2 things are multiplying by each other, if we have a pronumeral or now even a surd, I can write this 2 next to the root 3, and it implies that this is going to be 2 multiplied by root 3. So root 3 is a surd because 3 is not a perfect square. So when we multiply that by 2, we're going to get another irrational number. So this is going to be a surd. So if I have, for example, 2 root 3 and I add 3 root 3, let's look at what we end up getting. So think about this, because here my 2, as I said, I'm basically doing 2 lots of root 3 and I'm adding to that 3 lots of root 3. This looks kind of scary, but believe it or not, you have seen this before. What would we do, for example, if instead of this being 2 root 3, I wrote 2x plus 3x. Well, you would tell me, oh, I know this from algebra, so I know that I can just add these numbers together to give me 5x. We can do the exact same thing with surds. Because think about it, algebra tells us that if we have any pairs of numbers multiplying by the same pronumeral or the same number, because remember, x is just representative of any number. If I have 2 lots of one number, I add it to 3 lots of another number, algebra tells us I will get 5 lots of that number. So substituting any number into this, I'm always going to get 5 lots of that number. So that number in this case is root 3. I have 2 lots of root 3. I'm adding it to 3 lots of root 3. So I wind up with 5 lots of root 3. That is a property of surds. We can add or subtract them like we would in algebra. Let's look at another example. Let's make this a little trickier. If I had 3 root 7 minus root 6 plus 2 root 7. I've used 3 and 2 before. Let's say I have 5 root 7. Okay. How would I do something like this? Well, we said that we can treat this like we would with algebra, right? So instead of this, for example, let's say we had 3a minus, and instead of root 6, let's say, because here we have 1 lot of root 6. This is like saying 1 lot of root 6 or just root 6. This is like saying, for example, minus 1 lot of b or just minus b. And I'm adding, for example, 5a here. What would you do if this was an algebra question? Well, if you wanted to simplify this algebraic expression, you would group together your like terms. So you would say, okay, 3a plus 5a gives me 8a, and b is a different pronumeral, meaning a different number, so we can't simplify this anymore. So we would just leave it like this. The same thing gets done when we deal with surds, because the principles of algebra apply to any numbers. So even these irrational numbers, the patterns are still going to emerge. So if we dealt with this question here, we would still match the like terms together. So 3 lots of root 7 plus 5 lots of root 7 will give me 8 lots of root 7. And I'm subtracting root 6 from that. Now this cannot be simplified any further. So I'm going to actually make a note of that. So as in algebra, this can't be simplified further. We are finished. And if you actually pop this into your calculator, just for a thing to do at home, pop this thing into your calculator. So write 3 root 7 minus root 6 plus 5 root 7. And then also put in 8 root 7 minus root 6 and see what answer you get. You will find that you will get the same exact answer. It's going to be an irrational number, right? Because these are surds. Root 7, root 6 are not perfect squares. Well, the numbers 7 and 6 are not perfect squares. So we will get surds when we apply the square root. We will get an irrational number as an answer. You can even try this for the first example if you'd like. Pop this into your calculator and pop this into your calculator. See if you get the same thing. Now, another property of surds and any square root numbers is, this is just a key idea here. Now, we know this from what we did previously in when dealing with roots and powers. And this is that if we take the square root of a number and then we square that, we're going to get that number back. Think about this, right? Now let's actually prove this using what we learned about fractional indices. So this thing here, let's write here proof. So this is taking the square root of a. So using what we learnt about fractional indices, this is like saying the square root of a I can represent as a to the power of a half. And I'm squaring all of that. This gives me a to the power of, now remember, when we take the power of a power in indices, we can multiply the powers. So I'm doing a half times 2. When I multiply a half by 2, I get 1. So I get a to the power of 1, which equals a. So taking a to the power of 1 gives me a. So therefore, the square root of a number, or that number to the power of a half, these mean the same thing. If I square that, I get this number back. Now this idea is just a slight detour because we're going to use this to talk about, let me put a little red box over this, because we're going to use this to consider something interesting that happens with multiplying surds and dividing surds as well. So let's look here at multiplication. Okay, now what you guys typically see in your textbooks when you work through surds, this is something I found, it never really got explained. It was just something we sort of took for granted, and we'd write it in our calculators and we'd get back the same answer. So we thought, okay, well cool, this works, we can apply this to everything. We're just going to take a slightly closer look at this feature of surds. And this is the fact that when you multiply two numbers in separate square roots, you will get the same as saying the square root of these individual things multiplied together. So you can try this in your calculator, for example. You can say, all right, root 2 times root 3, and then see if that gives you the same answer as putting in root 6, which is 2 times 3. But we're going to take a closer look at this through a little exercise. Now, to think about proving this. So, I'm going to put this key idea in a nice big red rectangle, because we're going to do some questions to practice this too. But I want to think about this first. So, once again, we're going to come up with a proof for this, because you don't want to just take my word for it, right? Now, if this doesn't interest you and this is enough, sure, go right ahead and you can skip to some of the example questions I give. But the proof is nice because it really just summarizes what we are. It lets us understand why this actually works. So, I'm going to say, if I times some number by another number, if I take the square root of these, it's going to give me some answer. I don't care what that's going to be. Let's call that x. Okay, so I square root any number a, I multiply by the square root of any number b, and I get some answer x. Don't worry about what x is, it's just an answer, right? Now, what would happen, for example, if we squared both sides? So we're going to square both sides. And I'm going to wind up with x squared on this side, and I've done that in a slightly different color, I think. I'm going to square x on this side, and then I'm going to square this entire expression. So, from this thing on the left here, based on our previous feature of surds that we defined and proved, if I take the square of a square root, I just get, if I square root a number a, and then I square that, I'm going to get a back. So therefore, if I have the square root of a times b, if I have the square root of a times the square root of b and square all of that, then that's going to undo the square root. So I'm going to get left a times b here still equals my other number squared. Now, remember with algebra, we can shorten a times b into ab, and I can now take the square root of both sides, square root of both sides, and if I take the square root of x squared, well, we have the same principle. It's going to undo the squaring, and we're going to get left with that number. And if I square root ab, I'm going to get root ab. So here, x equals root of ab, and it also equals root a times root b. And we wind up with, therefore, root a times root b equals the root of ab. This is a feature of surds. This being that when we multiply two surds together, we can express this as the square root of the product of those two here. So if we had an example here, e.g. root 5 times root 3, well, I can express that as just the square root of 5 times 3. And that gives me the square root of 15 here. Let's do one more example with that. If I had, for another example, root 3 times root 10, that would give me, well, just the square root of 3 times 10, which is 30. And also, just to help us with the definition of our surd, this and this, both 15 and 30 are not perfect squares. So that means when I take the square root of 15 and 30, I'm going to get an irrational number. So both of these are surds. Now, extending this to the idea of division, I have a very similar thing happening. So if I have the square root of a divided by the square root of b, that's going to give me the square root of a divided by b. And the proof here is the exact same as for up here. So I can pretty much just copy and paste this, and I'm going to get a very similar thing happening. Let me quickly run through the proof. You can take a second to pause the video if you'd like, have a go at it on your own. But what I'm going to say here is that if I take the square root of a and I divide it by the square root of b, that's going to give me some answer x, right? Once again, squaring both sides, I'm going to get x squared, and I'm going to get root a divided by root b all squared. And then the squaring here is going to undo my square roots here. So I'm going to get that x squared equals to a divided by b. Now remember, algebra lets us write this in a shorthanded way. We write this as a fraction, So that would be A over B. And now I can just square root both sides. So I'm going to square root this side, I'm going to square root this side, and I get left with that same pronumeral x being equal to A over B, the square root of A over B. So therefore, because this this root A over B is equal to x, and these separately getting divided also equals to x, I can now say, therefore, root A divided by root B gives me the square root of A over B. And an example of this, because let's just do 2 to wrap up here. If I have the square root of 10 divided by the square root of 5, what do I get? Well, I'm going to get the square root of 10 divided by 5, which is going to be the square root of 2. That is once again a surd, because 2 is not a perfect square. So the square root of 2 will give us an irrational number. And one more here. If we took the square root of 24, divided that by the square root of 8, I get the square root of 24 divided by 8, and then that gives me the square root of 3, which is once again a surd. So these are all of the operations we've learnt back in primary school. You're adding, subtracting, multiplying, dividing. We can apply all of those to surds in these different ways. So one of the operations is division. And we identified this particular rule, that dividing one by the other is the same as just dividing those but under the same square root sign. We get a similar thing happening when we multiply. And we can do this for any questions now that you'll get in your textbook. And we have just a feature of surds, which is that, or any square roots and any square numbers, which is that if we have the square root of, for example, A here, and I square that, I get left with just that number A. In other words, the squaring undoes the square rooting. And also the final thing is that we can add and subtract surds and these kind of trickier surd expressions, sort of like this or the one down here. We can do this in the same way as we did with algebra. So let me write a little thing here for you guys, which is that surds can be simplified using addition or subtraction. Using addition or subtraction if they are what we call like surds. Where does that sound familiar? Well, you may have heard it from algebra. Remember, we talked about these like terms. So, for example, here, 3 root 7 and 5 root 7, because these coefficients 3 and 5 are both multiplying by the same number, that means that these are like surds. And we can add and subtract to simplify. And remember, we can't simplify any further if we don't have like terms or like surds. These are not like surds because they are different numbers. But that just wraps up all of the things you need to know about defining surds and then carrying out simple operations with surds as well. Thank you so much for watching, guys, and I'll see you in the next video.